This is a video for AQA Further Pure Mathematics, Matrices, section 5.7, finding m to the power n. Well, in previous videos we've developed the idea that a matrix can be diagonalized and written in the form V, D, V inverse, where V, remember, is made up of the eigenvectors and D is the matrix which is diagonal, made up of the corresponding eigenvalues along the leading diagonal. Now just consider what happens if we find m squared then. So m squared must be equal to V, D, V inverse multiplied by V, D, V inverse. But of course you see there that we get V, V inverse, which is the identity, so that this then simplifies to being V D squared V inverse. But that's going to happen whatever the power that we raise. So m to the power n will just be a series of these V D V inverses written out n times. And at each time we will have V, V inverse, and therefore this must be equal to V and then D to the power n V inverse. But what is important about this and how it makes life a lot easier for us is that D inverse is in fact very easy to find. Because if we have a diagonal matrix, and remember we've got lambda 1, lambda 2, etc. on the leading diagonal, so these are the values of the eigenvalues, then when we multiply that by itself, all that happens is that lambda 1 is squared, lambda 2 is squared, and lambda 3 is squared, with zeros everywhere else. And that would be true for an n by n matrix. So what we're saying is that all we need to do to work out the diagonal matrix to the power n is raise the values on the leading diagonal to the power n. So we have the idea that if m is equal to V D V inverse, so we've diagonalized the matrix, then the matrix to the power n is V D to the power n V inverse. And D to the power n is very easy to find because it is simply the elements on the leading diagonal raised to the power n. Let's look at that then for a particular one that we've already found. We've diagonalized the matrix 2, 2, negative 1, 5 in a previous video and found that it was equal to this. So this is the matrix V, this is the diagonal matrix, and this V inverse. So if we want to find m to the power 5, then m to the power 5 will be equal to V D to the power 5 V inverse. So that will be V, which is 2, 1, 1, 1. D to the power 5 is now very straightforward to calculate because we simply raise to the power 5 the elements which are on the leading diagonal, 3 to the power 5 and 4 to the power 5, and multiply that by the inverse 1, negative 1, negative 1, 2. So raising that diagonal to the power 5 then produces 243. That will then be 0, 0, and 4 to the power 5 is 1024. If you multiply out the first two of those matrices, you get 486, the first element, 1024, and then 243, and 1024. And that will be multiplied by V inverse, which is 1, negative 1, negative 1, 2. So finally, we end up with the following: negative 538, 1562, negative 781, and 1805. So the diagonalized matrix, which is VD to the power n V minus 1 when we raise it to the power n, becomes straightforward to calculate, because this diagonal matrix here to the power n is just the elements on the leading diagonal raised to the power. Admittedly, these are large numbers we're dealing with here. However, it's much simpler and much faster than raising the original matrix, which is 2 to negative 1, 5 to the power 5. You'd have lots of calculations to do there. And of course, this is no more difficult if it was power 9 or power 13. Any power indeed we can do in this way. Likewise, a similar process for 3 by 3 matrices, or indeed matrices of any order that are square. Well, that concludes this video on how we find m to the power n, and indeed concludes the series of videos looking at eigenvectors and eigenvalues.